Hello and welcome to the deep Somna. Welcome to tonight's journey through the ocean. Find a comfortable position, let your body settle, and allow your breathing to slow. Over the next few hours, we'll explore 100 gentle facts about Earth's waters, the deep blue expanses that cover our planet, the creatures that inhabit them, and the quiet wonders that unfold beneath the waves. There's nothing you need to do except listen, rest, and let these peaceful discoveries wash over you like gentle tides. Let's begin. The ocean covers more than 70% of Earth's surface. If you could see our planet from space, you'd notice that blue dominates the view. Vast stretches of water that connect continents and wrap around islands. This immense coverage means that most of our world is, in a sense, underwater. The Pacific Ocean alone is larger than all the land masses combined. This shows how the ocean is not just a feature of Earth, but its defining characteristic. Earth is the only known planet with liquid water oceans. Among all the worlds we've discovered orbiting distant stars, and all the planets and moons in our own solar system, Earth stands alone in having stable, liquid seas on its surface. Mars may have had oceans billions of years ago, and some moons like Europa hold water beneath thick ice, but Earth's oceans exist in the open, bathed in sunlight, teeming with life. This uniqueness makes our blue planet a rare jewel in the cosmos. The ocean formed more than 4 billion years ago. In Earth's early years, the planet was a molten, hostile place. As it cooled, water vapor trapped in the atmosphere began to condense. Rain fell for millions of years, pooling in low places, filling the basins that would become ocean floors. Some of that water came from comets and asteroids that struck the young Earth. This means that the ocean is almost as old as the planet itself. The ocean is, in essence, one continuous body of water. Though we've given different regions names, the Atlantic, Pacific, Indian, Arctic, and Southern Oceans, these divisions are human inventions. Water flows freely between them, carried by currents that circle the globe. A molecule of water in the Atlantic today might drift to the Pacific in a few centuries. This interconnectedness shows how the ocean is a single, planetary system. More than 80% of the ocean remains unexplored. Despite centuries of seafaring and decades of modern technology, we've mapped and studied only a fraction of the ocean floor. The deep sea is less known than the surface of the Moon or Mars. Vast regions have never been visited by humans or even by our robots. This highlights how much mystery still lies beneath the waves. The ocean floor has mountains taller than Everest. The Mauna Kea volcano in Hawaii rises more than 10,000 meters from the ocean floor to its peak higher than Mount Everest rises above sea level. Most of this giant mountain is submerged. Underwater mountain ranges called mid-ocean ridges stretch for thousands of kilometers, forming the longest continuous mountain chains on Earth. These hidden peaks and valleys shape the ocean's geography in ways we rarely see. The deepest point in the ocean is the Challenger Deep in the Mariana Trench. It lies nearly 11 kilometers below the surface, far deeper than Mount Everest is tall. If you placed Everest at the bottom of the Challenger Deep, more than 2 kilometers of water would still cover its peak. The pressure there is immense, more than 1,000 times the atmospheric pressure at sea level. This extreme environment shows the ocean's incredible depth. Sunlight penetrates only the upper layers of the ocean. Light fades rapidly as you descend. By about 200 meters down, most sunlight has been absorbed. below 1,000 meters, the ocean is completely dark. This divides the ocean into the sunlit zone, where photosynthesis can occur, and the deep sea, where life exists without direct sunlight. This means that most of the ocean is a realm of perpetual night. The ocean contains about 97% of Earth's water. Fresh water exists in rivers, lakes, glaciers, and underground aquifers, but it makes up only a small fraction of the planet's total water. The ocean holds the vast majority. This saltwater reservoir is the ultimate source of the water cycle evaporation from the sea forms clouds, which bring rain to the land, which flows back to the sea. This cycle connects the ocean to every ecosystem on Earth. Seawater is salty because of minerals dissolved from rocks. Over millions of years, rain and rivers have carried minerals from the land into the ocean. Sodium and chloride, the components of common salt, are the most abundant. Volcanic activity on the ocean floor also contributes minerals. The saltiness, or salinity, varies slightly from place to place, but on average, seawater is about 3.5% salt. This dissolved salt gives the ocean its distinctive taste and its ability to support certain kinds of life. The ocean holds more than 50 times as much carbon dioxide as the atmosphere. Carbon dissolves in seawater, where it can form compounds like bicarbonate. This makes the ocean a crucial part of Earth's carbon cycle. By absorbing carbon dioxide, the ocean helps regulate the planet's climate. Phytoplankton in the sunlit surface waters also use carbon dioxide for photosynthesis, much like plants on land. This means the ocean acts as both a storage reservoir and a living system for processing carbon. Ocean temperatures vary widely from the surface to the depths. In tropical regions, surface waters can reach 30 degrees Celsius or warmer, but as you descend, the temperature drops. In the deep ocean, far from sunlight's warmth, the water hovers just above freezing, typically around 2 to 4 degrees Celsius. This cold, stable environment has existed for millions of years. It shows how the ocean contains many different temperature zones, each hosting distinct forms of life. The ocean has layers, each with its own characteristics. The surface layer, warmed by the sun, sits atop cooler water below. Beneath that lies the thermocline, a zone where temperature drops rapidly with depth. Deeper still, the temperature stabilizes in the cold abyss. Salinity and density also create layers. These layers influence how water moves and mixes, shaping ocean currents and nutrient distribution. This layering makes the ocean a complex, three-dimensional environment. Ocean currents act like rivers within the sea. Surface currents, driven by wind, carry warm water from the equator toward the poles, and cold water back toward the tropics. Deep currents, driven by differences in temperature and salinity, flow slowly through the ocean's depths. Together, these currents form a global conveyor belt that distributes heat around the planet. This circulation influences weather patterns and climate on every continent. The Gulf Stream carries warm water from the Gulf of Mexico across the Atlantic toward Europe. This powerful current moves as much water as all the world's rivers combined. It warms the climate of Western Europe, making places like the British Isles milder than other regions at the same latitude. The Gulf Stream is just one part of the ocean's vast circulatory system. This shows how ocean currents can shape the climate of entire continents. Tides are caused by the gravitational pull of the moon and the sun. The moon's gravity pulls on Earth's water, creating a bulge on the side facing the moon and another on the opposite side. As Earth rotates, these bulges move, causing the water level to rise and fall along coastlines. The sun also exerts a gravitational pull, though weaker than the moon's. When the moon and sun align, their combined pull creates especially high and low tides called spring tides. This rhythmic rise and fall has shaped coastal life for billions of years. Tidal ranges vary greatly depending on location. In some places, the difference between high and low tide is barely noticeable, just a few centimeters. In other locations, such as the Bay of Fundy in Canada, tides can rise and fall by more than 15 meters. The shape of the coastline and the depth of the water influence how tides behave. This variation means that tides create different environments in different parts of the world. Waves are created by wind blowing across the ocean's surface. As wind moves over water, it transfers energy, causing the water to rise and fall. The size of a wave depends on the wind's speed, how long it blows, and the distance over which it blows. In calm weather, waves are gentle ripples. In storms, they can tower many meters high. Waves carry energy across vast distances, sometimes traveling thousands of kilometers before reaching shore. This means that a wave breaking on a beach may have originated from a storm far out at sea. Tsunamis are not caused by wind, but by movements of the Earth itself. Underwater earthquakes, volcanic eruptions, or landslides can displace huge volumes of water, creating waves that travel at high speeds across the ocean. In deep water, a tsunami might pass unnoticed, just a gentle rise and fall. But as it approaches shallow coastal waters, it slows and grows in height, sometimes forming a devastating wall of water. This highlights the ocean's connection to the solid earth beneath it. The ocean floor is not flat, but varied and dynamic. It features deep trenches, towering mountain ranges, broad plains, and volcanic peaks. Mid-ocean ridges mark places where tectonic plates are pulling apart, and new seafloors being formed from molten rock rising from below. Trenches mark places where one tectonic plate slides beneath another. This activity means the ocean floor is constantly being created and destroyed, renewed over millions of years. Hydrothermal vents on the ocean floor spew superheated water. These vents form where seawater seeps into cracks in the Earth's crust, gets heated by underlying magma, and then erupts back into the ocean. The water can reach temperatures exceeding 300 degrees Celsius, but the immense pressure keeps it from boiling. These vents release minerals that precipitate out, forming chimney-like structures. This shows that even in the deep, dark ocean, geological forces are at work. Life thrives around hydrothermal vents despite the harsh conditions. Instead of relying on sunlight, the ecosystems here are based on chemosynthesis. Bacteria use the chemicals in the vent fluids as an energy source, forming the base of a food web. Tube worms, clams, and shrimp cluster around the vents, feeding on the bacteria or on one another. These communities exist in complete darkness, miles below the surface. This means that life can flourish in places once thought impossible to inhabit. Seamounts are underwater mountains that rise from the ocean floor. Most are extinct volcanoes. Some come close to the surface, while others remain far below. Seamounts create unique habitats, disrupting ocean currents and bringing nutrients upward. This attracts fish, corals, and other organisms. Many seamounts are biodiversity hotspots, home to species found nowhere else. This highlights how the ocean's topography creates pockets of life, even in the middle of vast, open waters. The ocean is ancient, but it is also constantly changing. Over geological time, ocean basins have opened and closed as continents drifted. Millions of years ago, a vast ocean called Tethys once separated the northern and southern land masses. As continents collided, Tethys disappeared, and its remnants became the Mediterranean Sea and other smaller bodies of water. The Atlantic Ocean, meanwhile, is still growing, spreading apart along the mid-Atlantic ridge. This means that the ocean's shape and size evolve on timescales far beyond human experience. Plate tectonics drives the movement of continents and ocean floors. Earth's outer shell is divided into large plates that float on the semi-fluid mantle below. These plates move slowly, only a few centimeters per year. Where they pull apart, new ocean floor forms. Where they collide, mountains rise or one plate dives beneath another. This movement has shaped the ocean basins and the distribution of land and sea over hundreds of millions of years. It shows that the planet's surface is dynamic, not fixed. Ancient oceans were different from today's. Hundreds of millions of years ago, the ocean was warmer and shallower in many places. Sea levels have risen and fallen throughout Earth's history as ice ages came and went. The chemistry of seawater has changed. Two early oceans had different levels of oxygen, salt, and minerals. These shifts influenced which forms of life could survive and evolve. This means that the ocean we see today is just one chapter in a much longer story. The first life on Earth likely arose in the ocean. Billions of years ago, simple organisms appeared in the seas, possibly near hydrothermal vents or in shallow, sunlit pools. These early microbes were the ancestors of all life. Over time, they evolved into more complex forms. For most of Earth's history, life existed only in the ocean. Land remained barren until plants and animals eventually made the transition from sea to shore. This highlights the ocean's role as life's cradle. Photosynthetic organisms in the ocean produce the oxygen in our atmosphere. Cyanobacteria, also called blue-green algae, began using sunlight to convert carbon dioxide and water into energy, releasing oxygen as a byproduct. Over hundreds of millions of years, this oxygen accumulated in the atmosphere, transforming the planet. It allowed the evolution of complex, oxygen-breathing animals. Even today, phytoplankton in the ocean produce about half of the world's oxygen. This means that every other breath you take comes from the sea. Fossils found in ancient ocean rocks tell us about life's history. Layers of sediment on the ocean floor have preserved the remains of countless organisms, shells, bones, and even impressions of soft-bodied creatures. By studying these fossils, scientists can trace how life evolved, how climates changed, and how mass extinctions reshaped the living world. These rocks are archives of deep time. This shows how the ocean floor holds clues to Earth's past. Phytoplankton are microscopic plants that drift in the sunlit surface waters. Though invisible to the naked eye individually, they exist in staggering numbers. These tiny organisms use sunlight to photosynthesize, forming the base of the ocean's food web. Zooplankton, Small animals feed on phytoplankton. Small fish eat zooplankton. Larger fish eat the smaller ones. This chain continues upward to apex predators like sharks and orcas. This means that nearly every animal in the ocean depends, directly or indirectly, on these drifting microscopic plants. Plankton come in countless varieties. Some phytoplankton are single-celled algae, others are bacteria. Zooplankton include tiny crustaceans, larvae of larger animals, and jellyfish relatives. Some plankton spend their entire lives drifting. Others are the juvenile forms of creatures that will grow into fish or crabs. This diversity means that the plankton community is constantly changing, shifting with seasons and currents. Jellyfish are among the ocean's most ancient animals. They have existed for at least 500 million years, long before the first fish appeared. Jellyfish have no brain, no heart, and no bones. Their bodies are mostly water, with a simple nerve net to sense their surroundings. They drift with currents, using stinging tentacles to capture prey. Despite their simplicity, jellyfish have thrived through countless environmental changes. This shows how even basic body plans can be remarkably successful. Some jellyfish may be biologically immortal. The species Turritopsis dohrnii can revert to an earlier stage of its life cycle after reaching maturity. Instead of dying, it transforms back into a polyp, a simpler form, and then grows again. In theory, this process could repeat indefinitely. Whether any individual actually lives forever is unknown, but the ability exists. This highlights the surprising flexibility of life in the ocean. Corals are animals, not plants, though they often resemble colorful underwater gardens. Each coral is a colony of tiny polyps, related to jellyfish and anemones. These polyps secrete calcium carbonate, forming hard skeletons that build up over time into reefs. Corals live in partnership with photosynthetic algae called zooxanthellae, which live inside their tissues. The algae provide the coral with food through photosynthesis, while the coral provides the algae with shelter. This mutualism allows reefs to flourish in nutrient-poor tropical waters. Coral reefs are among the most biodiverse ecosystems on Earth. Though they cover less than 1% of the ocean floor, they support about a quarter of all marine species. Fish, mollusks, crustaceans, sponges, and countless other organisms live among the coral branches. Reefs provide food, shelter, and breeding grounds. They are often called the rainforests of the sea. This shows how a single type of organism can create habitat for thousands of others. Reefs grow slowly, building up over thousands of years. A coral colony might grow just a centimeter or two per year. Over millennia, generations of corals build upon the skeletons of their predecessors, forming massive structures. The Great Barrier Reef, the largest reef system on Earth, stretches more than 2,000 kilometers along Australia's coast. It took roughly 20,000 years to form. This means that the reefs we see today are monuments built by countless generations of tiny animals. Sponges are among the simplest multicellular animals. They lack organs, a nervous system, or even true tissues. Instead, they filter water through their porous bodies, extracting tiny food particles. Water enters through small holes, passes through chambers lined with specialized cells, and exits through larger openings. A single sponge can filter thousands of liters of water each day. This efficient system has allowed sponges to thrive for over 600 million years. Some sponges live for centuries or even millennia. In the cold, deep waters of the polar regions, certain glass sponges grow extremely slowly and can live for thousands of years. These ancient organisms are among the longest-lived animals on Earth. Their longevity is possible because they live in stable, cold environments where they face few predators and little disturbance. This shows how the deep ocean can host organisms that experience time on a scale vastly different from our own. Sea anemones look like flowers but are predatory animals. They attach to rocks or coral and extend their tentacles, which are armed with stinging cells called nematocysts. When a small fish or shrimp brushes against the tentacles, the nematocysts fire, injecting venom and trapping the prey. The anemone then pulls the food to its mouth. Some anemones form partnerships with clownfish, which are immune to the stings and live among the tentacles for protection. This relationship benefits both species. Clownfish and anemones share a mutualistic bond. The fish gains a safe home, sheltered from predators by the anemone's stings. In return, the clownfish drives away predators that might eat the anemone and brings food scraps. The fish also helps keep the anemone clean. This partnership is so close that clownfish rarely stray far from their host. This shows how cooperation between species can shape behavior and survival in the ocean. Octopuses are among the most intelligent invertebrates. They have large brains and complex nervous systems. Octopuses can solve puzzles, open jars, and navigate mazes. They use tools, such as carrying coconut shells for shelter. They can also change color and texture in an instant, blending with their surroundings or communicating with other octopuses. Despite living only a few years, they display behaviors that suggest problem-solving and learning. This highlights the diversity of intelligence in the ocean. Octopuses have 3 hearts and blue blood. 2 hearts pump blood to the gills, where it picks up oxygen. The 3rd pumps blood to the rest of the body. Their blood contains a copper-based molecule called hemocyanin, which is more efficient at transporting oxygen in cold, low-oxygen environments than the iron-based hemoglobin found in vertebrates. This adaptation suits their often chilly habitats. It shows how different evolutionary paths can solve the same problem, delivering oxygen to cells in different ways. Squid and cuttlefish are relatives of the octopus. They also have flexible bodies, color-changing skin, and intelligent behaviors. Squid can swim quickly using jet propulsion, expelling water through a siphon. Some species are tiny, just a few centimeters long. Others, like the giant squid, can reach lengths of more than 10 meters. Cuttlefish are masters of camouflage, able to mimic complex patterns on the seafloor. These cephalopods demonstrate the range of body plans within a single group. This diversity allows them to occupy many different niches. The giant squid was once a creature of myth. Sailors told tales of enormous tentacled monsters attacking ships. For centuries, no one had clear evidence these creatures existed. But in recent decades, giant squid have been found washed ashore or caught in fishing nets. In 2004, researchers captured the first photographs of a living giant squid in its deep-sea habitat. These elusive animals live far below the surface, rarely encountered by humans. This means that even large animals can remain hidden in the ocean's vastness. Many deep-sea creatures produce their own light through bioluminescence. Chemical reactions within their bodies generate a glow, often blue or green. Some fish use light to attract prey, dangling a glowing lure in front of their mouths. Others use it to communicate with potential mates or to startle predators. In the darkness of the deep ocean, bioluminescence serves many purposes. This adaptation shows how life has found ways to illuminate the depths. The anglerfish uses a glowing lure to hunt. A modified spine extends from its head, tipped with a light-producing organ. In the pitch-black water, the glow attracts curious prey, which the anglerfish then swallows whole with its large mouth. Female anglerfish are much larger than males. In some species, the tiny male fuses to the female's body, becoming a permanent parasite that provides sperm when needed. This extreme reproductive strategy ensures that mates can find each other in the vast, dark ocean. Lanternfish are small but incredibly numerous. They live in the ocean's midwater zone, typically between 200 and 1,000 meters deep. At night, they migrate upward to feed on plankton, returning to the depths during the day. This daily migration, called diel vertical migration, is one of the largest movements of biomass on Earth. Billions of lanternfish make this journey every day. This means that enormous numbers of animals are constantly moving up and down through the water column. Sharks have been swimming in the oceans for over 400 million years. They predate most fish, trees, and even dinosaurs. Their basic body plan has remained remarkably successful. Sharks have skeletons made of cartilage, not bone, which is lighter and more flexible. Their skin is covered with tiny tooth-like scales that reduce drag as they swim. Sharks have keen senses, able to detect electrical fields generated by the muscles of other animals. This ancient lineage shows how effective design can persist across eons. Great white sharks are apex predators, but they are not mindless killers. They play an important role in maintaining the balance of marine ecosystems by controlling populations of seals, fish, and other prey. Great whites can grow to more than 6 meters long and travel vast distances across the ocean. They are curious and cautious, often investigating unfamiliar objects before deciding whether to bite. This behavior shows that sharks are complex animals, not simply eating machines. Whale sharks are the largest fish in the ocean. Despite their name, they are not whales but sharks. They can grow up to 18 meters or more in length. Whale sharks are gentle giants, filtering plankton and small fish from the water as they swim. They pose no threat to humans and are often observed by divers in warm tropical waters. Their size and their peaceful feeding style make them emblematic of the ocean's grandeur. This shows that the largest animals are often the gentlest. Manta rays glide gracefully through the water, propelled by large wing-like fins. These rays can have a wingspan of up to 7 meters. Like whale sharks, they are filter feeders, consuming plankton as they swim. Manta rays are intelligent and curious, sometimes approaching divers. They have the largest brain of any fish. This combination of size, grace, and intelligence makes them among the ocean's most captivating creatures. Sea turtles have been around for over 100 million years. They survived the extinction event that wiped out the dinosaurs. Sea turtles spend most of their lives in the ocean, but females return to sandy beaches to lay eggs. They often return to the same beach where they were born, navigating across thousands of kilometers of open ocean, using Earth's magnetic field as a guide. This remarkable homing ability shows how animals can navigate using senses we are only beginning to understand. There are 7 species of sea turtles, each with its own habits and range. The leatherback is the largest, capable of diving to depths of over 1,000 meters. Green turtles are named for the color of their fat, which comes from their herbivorous diet of seagrass and algae. Loggerheads have powerful jaws for crushing shellfish. Each species plays a different role in marine ecosystems. This diversity highlights the many ways life can adapt to the ocean. Seals and sea lions are mammals that return to the ocean. Their ancestors were land animals, but over millions of years, they adapted to life in the water. Their bodies became streamlined, their limbs transformed into flippers, and they developed the ability to hold their breath for long periods. Yet they still breathe air, give birth on land or ice, and nurse their young with milk. This shows how evolution can reshape a body plan to suit a new environment. Whales are the largest animals ever to have lived. The blue whale can reach lengths of over 30 meters and weigh more than 200 tons. No dinosaur, no land animal, no creature in Earth's history matches this size. Blue whales feed on tiny krill, filtering vast quantities of water through baleen plates in their mouths. Despite their size, they are gentle and graceful, gliding through the ocean with slow, powerful strokes of their tails. This immense scale is made possible by the buoyancy of water, which supports their weight. Whales communicate across vast distances using sound. Blue whales produce low-frequency calls that can travel hundreds of kilometers through the ocean. Humpback whales sing complex songs that can last for hours, patterns that change over time and vary between populations. These songs may play a role in mating or social bonding. In the ocean, where visibility is limited, sound becomes the primary means of communication. This shows how whales have adapted to their acoustic environment. Dolphins are smaller relatives of whales, known for their intelligence and playful behavior. They live in social groups called pods, cooperating to hunt fish and protect one another. Dolphins use echolocation, emitting clicks and listening for echoes to navigate and find prey. They can recognize themselves in mirrors, a sign of self-awareness. They also display empathy, helping injured pod members. This complexity shows that intelligence is not unique to humans or even to primates. Orcas, or killer whales, are actually the largest members of the dolphin family. They are apex predators, hunting fish, seals, and even other whales. Orcas live in stable family groups, passing down hunting techniques and vocal dialects through generations. Different populations specialize in different prey, developing unique strategies. Some hunt seals, and some target large whales. This cultural transmission of knowledge shows how learned behavior shapes survival in the ocean. Manatees and dugongs are gentle marine mammals that graze on seagrass. They are slow-moving and docile, drifting through shallow coastal waters and estuaries. Manatees live in the Atlantic and Caribbean, while dugongs inhabit the Indian and Pacific Oceans. Both are sometimes called sea cows because of their herbivorous diet and calm demeanor. They have few natural predators, though they face threats from boat strikes and habitat loss. This shows that even large, peaceful animals can be vulnerable, Penguins are flightless birds that have adapted to life in the ocean. They cannot fly through the air, but they swim with grace and speed, using their wings as flippers. Penguins hunt fish and krill, diving to depths of over 500 meters in some species. Emperor penguins, the largest, breed on Antarctic ice during the harsh winter, enduring months of cold and darkness. This extreme adaptation shows how versatile the basic bird body plan can be. Seabirds spend most of their lives at sea, returning to land only to breed. Albatrosses can glide for hours without flapping their wings, riding wind currents over the open ocean. Frigate birds have the largest wingspan to body weight ratio of any bird, allowing them to stay aloft almost continuously. Gulls, terns, and pelicans dive into the water to catch fish. These birds connect the ocean to the sky, showing how life can thrive at the interface between two environments. Kelp forests grow in cold, nutrient-rich coastal waters. Giant kelp can grow up to 60 centimeters per day, reaching lengths of more than 40 meters. These towering algae create underwater forests that provide habitat for countless species. Fish hide among the fronds. Sea otters wrap themselves in kelp to keep from drifting while they sleep. Sea urchins graze on the kelp, and when urchin populations grow too large, they can destroy entire forests. This shows how the balance between species shapes ecosystems. Sea otters play a crucial role in maintaining kelp forests. They feed on sea urchins, controlling their numbers. When sea otters are present, urchin populations remain in check, and kelp forests thrive. When otters are absent, urchins can multiply, overgrazing the kelp and creating barren areas called urchin barrens. This dynamic highlights the concept of a keystone species, an organism whose presence has a disproportionate effect on its environment. It shows how interconnected ocean ecosystems are. Mangrove forests grow along tropical and subtropical coastlines, where saltwater meets land. Mangrove trees have adapted to survive in salty, waterlogged soil. Their roots arch above the water, providing anchor and allowing them to breathe. These tangled roots create sheltered nurseries for young fish, shrimp, and crabs. Mangroves also protect coastlines from erosion and storms, absorbing wave energy. They act as a bridge between terrestrial and marine ecosystems. This shows how trees can thrive even in the ocean's edge. Seagrass meadows cover large areas of shallow coastal waters. Unlike kelp, which are algae, seagrasses are true flowering plants that have adapted to life underwater. They produce flowers and seeds, just like land plants. Seagrass meadows provide food and shelter for many animals, including sea turtles, manatees, and fish. They also stabilize sediment and improve water quality. This highlights the diversity of plant life that has moved into the ocean. The ocean absorbs much of the sun's heat, moderating Earth's climate. Water has a high heat capacity, meaning it can absorb and store large amounts of energy without changing temperature quickly. This property allows the ocean to act as a thermal buffer. In summer, the ocean absorbs heat, keeping coastal regions cooler. In winter, it releases that heat, keeping them warmer. This moderating effect makes coastal climates milder than those far inland. Ocean currents distribute heat around the planet. Warm water flows from the tropics toward the poles, while cold water flows back toward the equator. This circulation, driven by wind, temperature, and salinity differences helps balance the planet's heat budget. Without it, the tropics would be even hotter and the poles even colder. This global heat distribution is essential to maintaining the climates that support life. It shows how the ocean is a key player in the Earth system. The ocean influences weather patterns far beyond the coast. Water evaporates from the ocean's surface, forming clouds. These clouds can drift over land, bringing rain to fields and forests. Hurricanes and typhoons form over warm ocean waters, drawing energy from the heat stored in the sea. When these storms make landfall, they release that energy as wind and rain. This means that the ocean is a driver of weather, not just a passive body of water. The El Niño and La Niña phenomena are driven by ocean-atmosphere interactions. Every few years, sea surface temperatures in the tropical Pacific Ocean change. During El Niño, the eastern Pacific warms, altering weather patterns worldwide. Some regions experience heavy rains and flooding, while others face drought. La Niña brings cooler temperatures in different patterns. These events show how changes in the ocean can influence climates across entire continents. The ocean has absorbed much of the carbon dioxide released by human activities. Since the Industrial Revolution, the burning of fossil fuels has added large amounts of carbon dioxide to the atmosphere. The ocean has acted as a buffer, absorbing about a third of this excess carbon. This absorption has slowed the rate of atmospheric warming. However, it has also led to changes in ocean chemistry. This shows the ocean's role in the global carbon cycle. When carbon dioxide dissolves in seawater, it forms carbonic acid, making the ocean more acidic. This process, called ocean acidification, is happening gradually but steadily. A more acidic ocean can affect organisms that build shells or skeletons from calcium carbonate, such as corals, mollusks, and some plankton. These structures become harder to form and easier to dissolve. This means that ocean chemistry is shifting in ways that could challenge many forms of marine life. The ocean stores vast amounts of heat. Over the past several decades, more than 90% of the extra heat trapped by greenhouse gases has been absorbed by the ocean. This has slowed the warming of the atmosphere, but has led to warmer ocean temperatures. Warmer water expands, contributing to sea level rise. It also affects marine life, as many species are adapted to specific temperature ranges. This shows how the ocean is both a mitigator and a victim of climate change. Sea level has risen and fallen many times throughout Earth's history. During ice ages, sea level dropped as water was locked up in glaciers. During warmer periods, glaciers melted and sea level rose. Today, sea level is rising due to the thermal expansion of warming water and the melting of ice sheets in Greenland and Antarctica. This rise is gradual but persistent, and it will continue for centuries even if greenhouse gas emissions are reduced. This highlights the long-term legacy of changes already underway. Ice sheets and glaciers on land hold enough water to raise sea level by many meters. If all the ice on Greenland melted, sea level would rise by about 7 meters. If the Antarctic ice sheet melted entirely, the rise would be over 50 meters. These events would take centuries or millennia to occur, but they illustrate the ocean's potential to change dramatically. This shows the immense volume of water stored on land in frozen form. The Arctic Ocean is warming faster than other parts of the world. Sea ice, which floats on the surface, is declining in extent and thickness. This loss of ice has consequences beyond the Arctic. Ice reflects sunlight, helping to keep the region cool. As ice melts, darker ocean water absorbs more heat, accelerating warming. Arctic warming also affects weather patterns at lower latitudes. This shows how changes in one part of the ocean can ripple outward. The Antarctic Ocean, also called the Southern Ocean, encircles Antarctica. Its cold, nutrient-rich waters support a rich food web. Krill, small shrimp-like crustaceans, are abundant here. They feed on phytoplankton and are in turn eaten by fish, seals, penguins, and whales. Antarctic krill are among the most numerous animals by biomass on Earth. This shows how a single species can be the cornerstone of an entire ecosystem. Upwelling brings deep, nutrient-rich water to the surface. This process occurs where winds push surface water away from the coast, allowing deeper water to rise and replace it. Upwelling zones are among the most productive regions of the ocean. Nutrients that had settled into the depths are brought back into the sunlit zone blooms of phytoplankton. Fish and seabirds flock to these areas to feed. This shows how physical processes can create oases of life in the open ocean. Oxygen minimum zones exist in parts of the ocean where oxygen levels are very low. These zones typically occur in the mid-water depths, where decomposition of organic matter consumes oxygen faster than it can be replenished. Some animals have adapted to survive in these low-oxygen environments. Certain fish and squid can slow their metabolism or extract oxygen more efficiently. This highlights the range of conditions life can tolerate. Dead zones are areas where oxygen levels have dropped so low that most marine life cannot survive. These zones are often caused by nutrient pollution from agricultural runoff. Excess nutrients fuel massive algae blooms. When the algae die and decompose, bacteria consume the oxygen in the water. Fish and other mobile animals flee, while immobile creatures suffocate. Dead zones can cover thousands of square kilometers. This shows how human activities on land can have far-reaching effects on the ocean. Marine snow is a continuous rain of organic material falling from the surface to the deep ocean. It consists of dead plankton, fecal pellets, and other detritus. As it sinks, it provides food for organisms at various depths. The material that reaches the ocean floor feeds deep-sea creatures and gets buried in sediment, locking away carbon for millions of years. This process is part of the ocean's biological pump, which helps regulate atmospheric carbon dioxide. It shows how life in the surface waters feeds life in the depths. The deep sea is the largest habitat on Earth. It covers more than half the planet's surface and holds the majority of its living space. Yet it is also one of the least studied. The deep ocean is cold, dark, and under immense pressure. Food is scarce, arriving mostly as marine snow drifting from above. Despite these challenges, life has found ways to thrive. This shows the resilience and adaptability of living organisms. Deep-sea fish often have bizarre adaptations. Some have enormous mouths to catch rare prey. Others have transparent bodies or bioluminescent lures. Many have reduced or absent eyes, as vision is useless in total darkness. Some rely on other senses, such as detecting vibrations or chemical signals. These adaptations reflect the extreme conditions of the deep sea. They highlight how evolution shapes organisms to fit their environment. Tube worms at hydrothermal vents can grow over 2 meters long. They lack mouths and digestive systems. Instead, they house bacteria inside their bodies. These bacteria convert chemicals from the vent fluids into energy, which the worms absorb. In return, the worms provide the bacteria with a safe place to live and access to vent chemicals. This symbiosis allows both organisms to thrive in a place where no sunlight reaches. It shows how life can create complex partnerships to survive in extreme environments. Cold seeps are similar to hydrothermal vents, but release cold, methane-rich fluids instead of hot water. These seeps occur where methane gas escapes from the seafloor. Bacteria at cold seeps use the methane as an energy source, forming the base of a food web. Clams, mussels, and tube worms live in clusters around the seeps. This shows that chemosynthesis can support diverse ecosystems. Humans have explored the ocean for thousands of years. Ancient Polynesians navigated vast stretches of the Pacific using stars, waves, and bird behavior, settling remote islands long before the age of European exploration. Phoenician sailors ventured far from the Mediterranean coast. Chinese treasure fleets crossed the Indian Ocean. These early voyages show that the ocean has always been a highway, not a barrier. The invention of the diving bell allowed humans to descend below the surface. Early diving bells were simple chambers filled with air, lowered into the water. They allowed workers to repair ship hulls or salvage cargo. Over time, technology improved. Scuba gear, developed in the mid-20th century, gave divers freedom to move underwater. Submersibles and remotely operated vehicles allowed exploration of the deep sea. Each advancement extended our reach into the ocean. The Challenger expedition in the 1870s was one of the first scientific voyages dedicated to studying the ocean. The crew traveled the globe, collecting samples of water, sediment, and marine life. They measured depths, temperatures, and currents. The expedition's findings filled dozens of volumes and laid the groundwork for the science of oceanography. This showed that the ocean could be studied systematically, not just navigated. Sonar technology, developed during the World Wars, allowed humans to map the ocean floor. By sending sound waves downward and measuring the time it took for echoes to return, ships could determine the depth of the water beneath them. This revealed underwater mountains, trenches, and plains that had never been seen. Today, detailed maps of the ocean floor help us understand tectonic activity, plan undersea cables, and locate shipwrecks. This shows how technology can unveil hidden landscapes. The first humans descended to the deepest part of the ocean in 1960. Oceanographer Jacques Piccard and U.S. Navy Lieutenant Don Walsh piloted the bathyscaphe to the bottom of the Challenger Deep. They spent just 20 minutes at the bottom before ascending. The journey took hours and required careful engineering to withstand the immense pressure. This historic dive proved that humans could reach even the most remote parts of the planet. Satellite technology has revolutionized ocean observation. Satellites can measure sea surface temperature, track ocean currents, monitor phytoplankton blooms, and detect changes in sea level. They provide a global view that would be impossible from ships alone. Data from satellites helps scientists understand climate patterns, predict weather, and track the health of marine ecosystems. This shows how space-based tools have become essential for studying the Earth below. The ocean is home to millions of species, most of which have not yet been described by science. New species are discovered regularly, from tiny crustaceans to large fish. The deep sea, in particular, holds countless unknowns. Each expedition returns with organisms that have never been seen before. This ongoing discovery shows how much we still have to learn about life on our own planet. Many traditional human communities depend on the ocean for their livelihoods. Fishermen, coastal farmers of seaweed, and pearl divers have intimate knowledge of local waters, passed down through generations. These communities have developed sustainable practices, harvesting resources without depleting them. Their knowledge complements scientific understanding and offers lessons in stewardship. This shows how human cultures and the ocean are deeply intertwined. Overfishing has depleted many fish populations. Industrial fishing fleets can catch enormous quantities of fish in a short time. Some fishing methods, such as bottom trawling, damage the seafloor. Species that were once abundant, such as cod in the North Atlantic, have declined sharply. When large predators are removed, ecosystems can shift, sometimes in unpredictable ways. This shows the impact humans can have when harvesting the ocean's resources without restraint. Marine protected areas are regions where fishing and other extractive activities are limited or banned. These areas give ecosystems a chance to recover. Fish populations can rebound, and damaged habitats can heal. Protected areas also serve as living laboratories, helping scientists understand how ecosystems function without heavy human interference. This shows that thoughtful management can help restore balance. Plastic pollution has become a visible problem in the ocean. Plastics from land bags, bottles, fishing gear are carried by rivers and wind into the sea. Once there, they break down into smaller and smaller pieces but do not disappear. Marine animals can mistake plastic for food or become entangled in debris. Microplastics, tiny fragments, have been found in the deepest trenches and in the bodies of animals throughout the food web. This shows how materials we use on land can end up far out to sea. Efforts to reduce ocean pollution are growing. Beach cleanups, bans on single-use plastics, and innovations in recycling are all steps toward a cleaner ocean. Some organizations are developing technologies to remove plastic from the sea. Public awareness is increasing. This shows that people recognize the problem and are working towards solutions. The ocean has inspired art, literature, and mythology across cultures. Ancient Greeks told stories of Poseidon, god of the sea. Polynesian legends spoke of ocean voyagers and sea creatures. Paintings of stormy seas captured the ocean's power. Novels like Moby Dick explored humanity's relationship with the marine world. The ocean continues to inspire music, film, and poetry. This shows how the ocean touches not just our survival, but our imagination and creativity. The sound of the ocean is a source of calm for many people. The rhythmic crash of waves, the distant call of seabirds, and the whisper of wind over water create a soundscape that many find soothing. The ocean's constancy, its endless motion, its vast presence can offer a sense of perspective. This connection shows how the ocean affects not just ecosystems and climate, but also human emotions and well-being. The ocean continues to surprise us. Scientists recently discovered that octopuses can edit their own genetic instructions in ways most animals cannot. Deep-sea corals have been found thriving in places once thought too dark and cold. New migration patterns, unexpected behaviors, and hidden connections between species are uncovered regularly. This ongoing revelation shows that the ocean remains a frontier, a place of wonder and mystery. Whale falls are ecosystems that form when a dead whale sinks to the ocean floor. The massive carcass provides food for scavengers, sharks, hagfish, crabs that strip away the flesh. Afterward, bacteria break down the bones, and specialized worms and mollusks colonize the skeleton. A single whale fall can sustain a community for decades. This shows how even death in the ocean supports life, cycling nutrients back into the system. The future of the ocean depends on choices made today. If greenhouse gas emissions continue unchecked, the ocean will continue to warm and acidify. Sea levels will rise. Ecosystems will shift. But if efforts to reduce emissions succeed, if pollution is curbed, and if sustainable practices are adopted, the ocean can remain resilient. This shows that the ocean's future is not fixed, but shaped by human actions. Restoration efforts are underway in many parts of the world. Coral reefs are being replanted with fragments of healthy coral. Mangrove forests are being restored along coastlines. Oyster reefs, which filter water and provide habitat, are being rebuilt. These projects show that damaged ecosystems can recover with care and effort. They offer hope that degradation is not irreversible. The ocean is a source of potential solutions. Seaweed farming can provide food and absorb carbon. Marine organisms have inspired medicines and materials. Offshore wind farms harness the ocean's winds for renewable energy. The ocean holds resources that, if used wisely, can help address global challenges. This shows that the ocean is not just something to protect, but also a partner in building a sustainable future. Education and awareness are key to ocean conservation. The more people understand about the ocean's importance, its beauty, and its vulnerability, the more likely they are to support policies that protect it. Documentaries, aquariums, and citizen science projects bring the ocean into people's lives, even those far from the coast. This connection fosters a sense of responsibility. It shows that caring for the ocean begins with knowing it. Indigenous knowledge offers valuable insights into ocean stewardship. Many coastal and island communities have managed marine resources sustainably for generations. Their practices, rooted in long-term observation and cultural values, emphasize balance and respect. Integrating this knowledge with modern science can lead to more effective conservation strategies. This shows that wisdom about the ocean comes from many sources. Children growing up today will inherit the ocean's future. They will see changes their grandparents could not have imagined. But they will also have tools and knowledge earlier generations lacked. Engaging young people in ocean science, conservation, and exploration can inspire the next wave of discovery and care. This shows that the ocean's story is ongoing, written by each new generation. The ocean connects all of us, no matter where we live. It produces oxygen we breathe, regulates the climate, provides food, and inspires awe. It is a reminder of the planet's complexity and beauty. To care for the ocean is to care for ourselves and for the countless forms of life that share this world. This connection shows that the ocean is not separate from us, but part of a single living system. The ocean is patient. It moves in cycles that span days, seasons, and millennia. It has witnessed the rise and fall of countless species, the drift of continents, and the slow dance of ice ages. It will continue long after our individual lives. This deep time perspective offers a kind of peace. It shows that we are part of something much larger than ourselves. On quiet nights, the ocean reflects the stars. The surface becomes a mirror, blending sea and sky. In those moments, the boundary between the two seems to dissolve. The ocean, which gave rise to life, carries within it the same elements forged in ancient stars. We are made of stardust and seawater, connected to the cosmos and the deep. This poetic truth shows that the ocean is not just a place, but a story of origins. The ocean invites exploration, not just with technology and science, but with imagination and wonder. To stand at the shore, to listen to the waves, to watch the horizon where water meets sky, is to touch something timeless. The ocean reminds us that there are mysteries we may never fully solve, depths we may never reach, and beauty we may never fully capture in words. And that is part of its gift. The ocean teaches patience. It shapes coastlines grain by grain, wave by wave, over centuries. It teaches resilience, weathering storms and always returning to calm. It teaches connection, linking every drop of water in an unbroken cycle. These lessons are subtle, but they are there for those who listen. This shows that the ocean is not just a resource, but a teacher. The ocean is never truly silent. Even in the deepest trenches, there is sound. The creak of the earth's crust, the clicks of hunting whales, the hum of distant currents. Life and geology create a symphony that fills the water. This hidden music shows that the ocean is alive in ways we often overlook, vibrant even in its quietest corners. The ocean is a reservoir of memory. In its sediments lie the remains of ancient creatures, the ash from long-extinct volcanoes, and the traces of climates past. Ice cores from glaciers fed by ocean moisture record thousands of years of atmospheric history. The ocean holds the archives of the planet. This shows that to study the ocean is to read the story of Earth itself. Every drop of water in the ocean has traveled. It has evaporated into clouds, fallen as rain, flowed through rivers, seeped into the ground, and returned to the sea. A single molecule may have cycled through this journey hundreds of times. It may have been drunk by a dinosaur, frozen in a glacier, or carried in the bloodstream of a whale. This endless circulation shows that water is a traveler, connecting all places and all times. The ocean is generous. It gives oxygen, food, beauty, and wonder. It asks nothing in return, only that we recognize its value and treat it with care. This generosity is not limitless, but it is vast. If we honor the ocean, it will continue to sustain life for generations to come. This shows that our relationship with the ocean is one of reciprocity. To fall asleep thinking of the ocean is to rest in the embrace of something ancient and constant. The ocean will be there tomorrow, rising and falling with the tides, carrying its cargo of life and sediment and light. It will be there in 100 years and in 1,000. It is larger than our worries, older than our civilizations, and more patient than we can imagine. This constancy offers comfort. And so, as we close this journey through 100 facts about the ocean, let the images linger. The shimmer of sunlight on waves, the silent drift of a jellyfish, the slow dance of kelp in the current, the call of a whale echoing through the deep, the endless horizon where sky and water meet. These are the gifts of the ocean, offered freely to all who seek them. The ocean floor contains mountain ranges that dwarf those on land. The Mid-Atlantic Ridge runs like a spine down the center of the Atlantic Ocean, stretching over 16,000 kilometers. It marks the boundary where tectonic plates pull apart, creating new oceanic crust. Volcanic activity along the ridge builds underwater mountains that occasionally break the surface as islands, such as Iceland. This hidden topography shows that the most dramatic landscapes on Earth lie beneath the waves. Submarine canyons carve deep channels into continental shelves. These underwater gorges can rival the Grand Canyon in size and depth. The Monterey Canyon off the coast of California descends more than 3 kilometers below sea level. Submarine canyons form through erosion by underwater avalanches called turbidity currents, which carry sediment from shallow waters into the deep. These canyons funnel nutrients and organic matter into the abyss, supporting unique communities of life. This shows how geological features shape the distribution of marine organisms. Methane hydrates, sometimes called fire ice, exist in deep ocean sediments. These are ice-like structures where methane molecules are trapped within a lattice of water molecules. They form under high pressure and low temperature. Vast reserves of methane hydrate lie buried beneath the ocean floor, holding more carbon than all known fossil fuel reserves combined. If released suddenly, this methane could affect global climate. This highlights a largely hidden component of Earth's carbon system. The ocean contains underwater lakes and rivers. In some places, extremely salty water is denser than the surrounding seawater and pools in depressions on the seafloor. These brine pools have distinct surfaces and shorelines visible on sonar. They are toxic to most marine life, yet specialized bacteria thrive at their edges. Submersibles have filmed these eerie underwater lakes, complete with what looks like breaking waves where brine meets regular seawater. This shows that the ocean holds landscapes within landscapes. Abyssal plains are among the flattest places on Earth. These vast, featureless regions cover much of the deep ocean floor, lying 4 to 6 kilometers below the surface. Sediment accumulates slowly here, settling like dust over millions of years, smoothing out the underlying topography. Life on the abyssal plains is sparse but present sea cucumbers, brittle stars, and microbes eke out existence in the sediment. This shows that even the most barren-seeming places support life. Underwater volcanoes, called seamounts, number in the tens of thousands. Most will never breach the surface. They rise from the ocean floor, creating isolated habitats. Currents striking a seamount are forced upward, bringing nutrients with them. This upwelling attracts fish and other animals. Some seamounts host unique species found nowhere else, having evolved in isolation. This shows how geological features create islands of biodiversity in the open ocean. Black smokers are a type of hydrothermal vent that spew dark, mineral-rich water. The smoke is actually particles of metal sulfides precipitating out of the superheated fluid as it meets cold seawater. Over time, these particles build chimneys that can grow several meters tall. The minerals deposited by black smokers have economic value: copper, zinc, and other metals accumulate around vents. This shows that the ocean floor holds resources, though extracting them raises environmental concerns. White smokers are hydrothermal vents that emit lighter-colored minerals. They form at slightly lower temperatures than black smokers and deposit different compounds, such as barium and calcium. The ecosystems around white smokers are similar to those at black smokers, relying on chemosynthetic bacteria. The variety of vent types shows that even within extreme environments, there is diversity in conditions and in the life they support. The ocean's deepest trenches are formed by subduction zones. Where one tectonic plate slides beneath another, the seafloor bends downward, creating a trench. The Mariana Trench, the deepest of all, was formed this way. Subduction zones are also sites of intense geological activity, generating earthquakes and volcanic arcs. The trenches themselves are narrow and steep, like scars in the ocean floor. This shows the dynamic forces that shape the planet's surface. Life exists even in the deepest trenches. Amphipods, small shrimp-like crustaceans, have been found at the bottom of the Mariana Trench. Snailfish have been filmed at depths exceeding 8 kilometers. These animals have adapted to crushing pressure, near freezing temperatures, and total darkness. Their bodies contain special proteins that maintain cell structure under pressure. This shows that life's boundaries extend further than once thought possible. The ocean contains sounds from both natural and human sources. Whales sing, dolphins click, shrimp snap their claws, and ice creaks as it breaks. But the ocean also carries the rumble of ships, the pings of sonar, and the booms of underwater construction. Sound travels efficiently in water, much farther than in air. This means that human-made noise can spread across ocean basins, potentially disturbing marine life that relies on sound for communication and navigation. This shows that the ocean's acoustic environment is increasingly shaped by human activity. Some fish produce sound by vibrating their swim bladders. Croakers, drums, and toadfish use this method to communicate, especially during mating. The sounds can be surprisingly loud. In some coastal areas, the collective noise of fish can be heard from boats above. This form of communication shows that the ocean is filled with voices, most of which go unheard by human ears. Pistol shrimp create one of the loudest sounds in the ocean. They snap a specialized claw so quickly that it forms a cavitation bubble, a tiny void in the water. When the bubble collapses, it produces a shock wave and a flash of light, stunning or killing small prey. The snap is louder than a gunshot at close range. This remarkable adaptation shows how even small creatures can generate powerful forces. The ocean influences the water cycle in profound ways. Water evaporates from the ocean, rises into the atmosphere, and forms clouds. These clouds travel over land, where they release rain or snow. This precipitation feeds rivers and lakes, which eventually flow back to the sea. Without the ocean, this cycle would be vastly diminished. Most of the rain that falls on land originates from the ocean. This shows how the ocean sustains freshwater ecosystems far from the coast. Sea spray carries nutrients and minerals into the atmosphere. Waves breaking on the surface eject tiny droplets into the air. These droplets contain salt, organic matter, and microorganisms. As they drift over land, they deposit these materials, sometimes enriching soils or contributing to cloud formation. Sea spray is one way the ocean interacts with the atmosphere and land. This shows that the boundaries between Earth's systems are porous. The color of the ocean varies depending on what lives in it. In regions rich with phytoplankton, the water takes on a greenish hue because of the chlorophyll in the algae. In nutrient-poor regions, the water appears deep blue, as there is little algae to scatter light. Sediment-laden coastal waters can look brown or gray. Satellite images can reveal these color differences, allowing scientists to track phytoplankton blooms from space. This shows how the ocean's appearance reflects its biological activity. The Sargasso Sea is a region of the Atlantic Ocean, defined not by land, but by currents. It lies in the middle of a circular current system called a gyre. The Sargasso is known for its floating mats of sargassum seaweed, which provide habitat for fish, crabs, and other animals. It is also one of the calmest parts of the ocean, with little wind or wave action. Ships have historically struggled in the Sargasso because of the lack of wind. This shows how ocean currents can create distinct regions with unique characteristics. Gyres are large, circular ocean currents that span entire ocean basins. There are 5 major gyres, 2 in the Atlantic, 2 in the Pacific, and 1 in the Indian Ocean. Gyres are driven by wind patterns and the Coriolis effect, which is caused by Earth's rotation. Water and floating debris can become trapped in the center of a gyre, where currents are weak. This has led to the accumulation of plastic in regions like the Great Pacific Garbage Patch. This shows how currents can concentrate materials over time. The Great Pacific Garbage Patch is not a solid island of trash, but a diffuse area where plastic debris is more concentrated than elsewhere. Most of the plastic consists of small fragments suspended in the water or floating just below the surface. Fishing nets, bottles, and microplastics make up much of the debris. The patch spans an area larger than many countries, though its exact size is difficult to measure. This shows the scale of plastic pollution in the open ocean. Microplastics are plastic particles smaller than 5 millimeters. They come from the breakdown of larger items, or are manufactured small, as in cosmetics and industrial abrasives. Microplastics have been found in every part of the ocean, from surface waters to deep-sea sediments. Marine animals ingest them, sometimes mistaking them for food. The long-term effects on marine life and human health are still being studied. This shows that plastic pollution is not just a visible problem, but a pervasive one. Filter-feeding animals are particularly vulnerable to microplastic ingestion. Whales, manta rays, and oysters filter large volumes of water to extract plankton. In the process, they also consume plastic particles. Studies have found microplastics in the digestive systems of many marine species, from tiny zooplankton to large fish. This shows how pollution enters and moves through the food web. The ocean has natural mechanisms for breaking down some pollutants. Bacteria can degrade oil, for example. After oil spills, certain microbes multiply and consume the hydrocarbons, converting them into less harmful substances. However, this process takes time, and some pollutants, like plastics and heavy metals, resist biological breakdown. This shows that while the ocean has some resilience, it cannot neutralize all human impacts. Coral bleaching occurs when corals expel their symbiotic algae. This happens when the corals are stressed, often by rising water temperatures. Without the algae, corals lose their color and their main source of food. Bleached corals are not dead, but they are weakened and more vulnerable to disease. If conditions improve, the algae can return. If stress continues, the corals die. This shows how corals are sensitive indicators of ocean health. Some corals are more resilient to bleaching than others. Scientists have found that corals in warmer or more variable environments sometimes tolerate heat stress better than those in stable conditions. This has led to research into coral resilience and the possibility of assisting coral adaptation through selective breeding or relocation. This shows that not all corals respond the same way to environmental change. Coral reefs support fisheries that feed millions of people. Many fish species spend part of their lives on reefs, using them as nurseries or feeding grounds. Healthy reefs produce more fish, benefiting both commercial and subsistence fisheries. When reefs degrade, fish populations decline, affecting food security and livelihoods. This shows the direct connection between reef health and human communities. Parrotfish play an important role in reef ecosystems. They graze on algae that grow on coral surfaces. By keeping algae in check, parrotfish prevent it from smothering corals. Parrotfish also bite off chunks of coral to access the algae inside, grinding up the coral skeleton with their beak-like teeth. They excrete the ground coral as fine sand. A single parrotfish can produce hundreds of kilograms of sand per year. This shows how one species can shape both the biology and geology of a reef. Sea urchins also graze on algae, and their populations can fluctuate dramatically. When predators like sea otters or lobsters are present, urchin numbers remain low, and kelp forests or coral reefs thrive. When predators are removed, urchins can multiply and overgraze, devastating the habitat. This shows the importance of top-down control in marine ecosystems. Symbiosis is common in the ocean. Many species depend on partnerships with others. Clownfish and anemones, cleaner fish and their clients, corals and their algae all are examples of mutualism, where both partners benefit. These relationships can be so tightly integrated that one species cannot survive without the other. This shows how interconnected life in the ocean is. Cleaner fish set up stations on reefs where larger fish come to be cleaned. The cleaner fish pick off parasites, dead skin, and debris from the bodies of their clients. The clients, even predatory fish, refrain from eating the cleaners. This remarkable truce benefits both parties. The cleaner gets food, and the client gets groomed. Some cleaner fish are so important that their removal causes changes in the health and behavior of other reef fish. This shows how even small fish can play outsized roles. Remoras attach themselves to sharks, whales, and other large animals using a modified dorsal fin that acts like a suction cup. They hitch rides, feeding on scraps from their host's meals, and sometimes eating parasites off the host's skin. The host tolerates the remora, gaining a small cleaning service. This partnership shows another form of symbiosis commensalism, where one species benefits and the other is neither helped nor harmed significantly. Electric fish use electricity for navigation, communication, and hunting. Sharks and rays can detect the faint electrical fields produced by the muscles and nerves of other animals. This sense, called electroreception, allows them to find prey buried in sand. Some rays can also produce stronger electric shocks to stun prey or defend themselves. The electric eel, though it lives in fresh water, is a famous example of this ability. This shows how animals have evolved senses beyond the familiar five. Bioluminescence evolved independently many times in the ocean. Jellyfish, squid, fish, bacteria, and even some sharks produce light. The chemistry varies. Some use the enzyme luciferase. The purposes vary too: attracting prey, deterring predators, finding mates, or camouflaging against the faint light filtering from above. This widespread convergence shows that light is valuable even in the darkest depths. Camouflage in the ocean takes many forms. Some animals change color to match their surroundings, like cuttlefish. Others have transparent bodies, making them nearly invisible. Countershading dark on top, light on the bottom helps fish blend in when viewed from above or below. Some deep-sea fish have light-producing organs on their undersides to match the faint light from above, erasing their shadow. This variety shows the many ways animals avoid being seen. Mimicry is another survival strategy. Some harmless species evolve to resemble dangerous or unpalatable ones, gaining protection. The mimic octopus can imitate the appearance and behavior of more than a dozen different species, from lionfish to sea snakes, depending on the threat it faces. This shape-shifting ability shows the complexity of predator-prey interactions. Schooling behavior helps fish avoid predators. By moving in tight, coordinated groups, fish create confusion for attackers. A predator may struggle to single out one individual from the swirling mass. Schooling also improves foraging efficiency and reduces drag while swimming. This shows how cooperation can be a survival strategy, even among animals that do not actively communicate. Migration is common in the ocean. Many species travel vast distances between feeding and breeding grounds. Salmon are born in freshwater rivers, migrate to the ocean to grow, and return to their natal streams to spawn. Sea turtles nest on specific beaches, sometimes crossing entire ocean basins to reach them. Gray whales travel more than 10,000 kilometers between feeding grounds in the Arctic and breeding lagoons in Mexico. This shows the ocean's role as a migratory corridor. Navigation during migration is a complex skill. Animals use multiple cues: the position of the sun and stars, Earth's magnetic field, ocean currents, and even smell. Salmon can detect the unique chemical signature of their home stream. Sea turtles appear to have a magnetic map, allowing them to return to the beaches where they hatched. This shows that animals perceive the world in ways humans are only beginning to understand. Eels undertake one of the most mysterious migrations. European and American eels are born in the Sargasso Sea. The larvae drift on currents to coastal rivers in Europe or North America, a journey that can take years. There they grow into adults. After many years in freshwater, mature eels return to the Sargasso to spawn and die. How they navigate back across the open ocean remains unclear. This enigma shows that the ocean still holds secrets. Many ocean animals have lifespans far longer than their terrestrial relatives. The Greenland shark may live for over 400 years, making it the longest-lived vertebrate known. Some deep-sea clams and tube worms can live for centuries. Cold temperatures, slow metabolism, and stable environments contribute to this longevity. This shows that time moves differently in the ocean's depths. Reproduction strategies in the ocean are diverse. Some animals, like sea turtles, lay thousands of eggs, relying on sheer numbers for some offspring to survive. Others, like certain sharks, give birth to a few well-developed young. Many fish release eggs and sperm into the water, leaving fertilization and development to chance. Some species change sex during their lives, starting as one sex and becoming another as they grow. This shows the flexibility of reproductive strategies in marine life. Hermaphroditism is common in marine invertebrates and some fish. Clownfish live in groups with a strict hierarchy. If the dominant female dies, the largest male changes sex to become the new female. Groupers can switch sex based on social conditions. Being able to change sex allows populations to maintain balanced sex ratios even when numbers are low. This shows how life adapts to the challenges of finding mates in the vast ocean. Parental care is rare in most fish, but it exists. Male seahorses carry fertilized eggs in a specialized pouch, nourishing them until they hatch. Some cichlids, though mostly freshwater, have marine relatives that guard their eggs and young. Octopuses, despite their short lives, dedicate their final months to guarding their eggs, often refusing to eat until they die shortly after the eggs hatch. This shows that even short-lived animals can exhibit complex behaviors. The ocean's food webs are intricate and interconnected. Energy flows from sunlight to phytoplankton, to zooplankton, to small fish, to larger fish, and so on. But the web is not a simple chain. Many animals eat at multiple levels. A tuna might eat squid, which eat fish, which eats zooplankton. Dead material sinks and feeds the deep sea. Nutrients released by decomposition rise again. This shows how energy and matter cycle through the ocean in complex patterns. Apex predators structure ecosystems from the top down. Sharks, orcas, and large fish control the populations of species below them. When apex predators are removed, cascading effects ripple through the ecosystem. Prey populations explode, overgrazing their own food sources. The entire system can shift to a new, often less diverse state. This shows the importance of maintaining complete food webs. Trophic cascades demonstrate how interconnected ocean life is. When sea otters were hunted nearly to extinction, sea urchin populations exploded and devoured kelp forests. When otters were protected and their numbers recovered, kelp forests returned. This chain reaction shows how the presence or absence of a single species can transform entire ecosystems. Nutrient cycles in the ocean depend on the movement of key elements. Nitrogen, phosphorus, iron, and other nutrients are taken up by phytoplankton, passed through the food web, and eventually sink as waste or dead organisms. Bacteria in the sediment break down organic matter, releasing nutrients back into the water. Upwelling, mixing, and currents bring these nutrients back to the surface. This cycling sustains life across the ocean. Iron is a limiting nutrient in some parts of the ocean. Without enough iron, phytoplankton cannot grow, even if other nutrients are abundant. Dust blown from deserts can carry iron far out to sea, fertilizing the surface waters. Some scientists have proposed adding iron to the ocean to stimulate phytoplankton growth and capture carbon dioxide. However, such interventions carry risks and are controversial. This shows the delicate balance of ocean chemistry. Nitrogen fixation is performed by certain bacteria that convert atmospheric nitrogen into forms that other organisms can use. These bacteria live freely in the water or in symbiosis with other organisms. They are crucial in nitrogen-poor regions, providing a source of this essential nutrient. This shows how even microscopic organisms drive fundamental processes that support all ocean life. The ocean contains layers of sound that act like invisible highways. Sound waves travel differently depending on temperature, salinity, and pressure. In some parts of the ocean, these factors create a channel where sound can travel for thousands of kilometers with little loss of energy. This is called the SOFAR channel, or deep sound channel. Whales may use this channel to communicate across vast distances. A call made in one ocean basin could theoretically be heard in another. This shows how the ocean's physical properties create communication networks. Sperm whales are the loudest animals on Earth. Their clicks can reach 230 decibels, loud enough to vibrate through a human body. These clicks are used for echolocation, allowing the whales to hunt squid in complete darkness at depths exceeding 2 kilometers. The whales can adjust the frequency and intensity of their clicks, creating a sophisticated sonar system. This shows how evolution has equipped animals with tools perfectly suited to their environment. The ocean's twilight zone, between 200 and 1,000 meters deep, is one of the least explored regions. Light fades to near darkness here, and pressure increases steadily. This zone is home to more fish biomass than any other part of the ocean. Lanternfish, bristlemats, and hatchetfish dominate, performing their nightly migrations to feed in surface waters. During the day, they retreat to the twilight zone to avoid predators. This shows that even regions we rarely see teem with life. Vampire squid inhabit the twilight zone and deeper waters. Despite their ominous name, they are gentle creatures that feed on marine snow-organic debris drifting down from above. Their bodies are covered with light-producing organs, and they have large eyes to capture what little light exists. When threatened, vampire squid can turn themselves inside out, displaying spines and glowing spots to confuse predators. This defensive display shows the creativity of survival strategies in the deep. Barrel-eye fish have transparent heads. Their eyes are tubular and point upward, allowing them to watch for prey silhouetted against the faint light from above. The transparent dome protects their eyes while giving them an unobstructed view. This bizarre adaptation was only discovered when living barrel-eye fish were observed in their natural habitat. This shows that the ocean continues to reveal anatomical wonders that challenge our understanding of what is possible. Hagfish are among the most primitive living vertebrates. They resemble eels but are not closely related to them. Hagfish have skulls but no true vertebrae. When threatened, they produce enormous quantities of slime, which can clog the gills of predators. A single hagfish can fill a bucket with slime in minutes. This defense mechanism is so effective that few animals will eat hagfish. This shows how even simple defenses can be remarkably successful. The slime produced by hagfish is being studied for practical applications. The fibers in the slime are incredibly strong and elastic. Researchers hope to replicate them to create new materials, everything from synthetic spider silk to bulletproof fabrics. This shows how studying marine life can lead to unexpected technological innovations. Nautiluses are living fossils, largely unchanged for hundreds of millions of years. They have chambered shells which they fill with gas to control their buoyancy. Nautiluses live in the deep waters of the Indo-Pacific, rising toward the surface at night to feed. Unlike their relatives, the octopuses and squid, nautiluses have external shells and simpler eyes. Their survival through mass extinctions shows the success of their ancient design. Coelacanths were thought to be extinct until a living specimen was caught off South Africa in 1938. These fish have fleshy, limb-like fins and were once thought to be closely related to the ancestors of land vertebrates. Coelacanths live in deep, rocky habitats and are rarely encountered. Their discovery reminded scientists that the ocean can hide even large animals for centuries. This shows that extinction is difficult to prove in the deep sea. Deep-sea gigantism is a phenomenon where animals grow much larger than their shallow water relatives. Giant squid, giant isopods, and Japanese spider crabs with leg spans of several meters all inhabit the deep. The reasons for this gigantism are not fully understood, but cold temperatures, scarce food, and lack of predators may play roles. This shows how environmental pressures shape the size and form of organisms. Japanese spider crabs have the longest leg span of any arthropod, reaching up to 4 meters from claw to claw. Despite their intimidating appearance, they are scavengers, feeding on dead animals and plant matter on the seafloor. They move slowly, walking on their long legs like underwater spiders. This shows that size in the ocean does not always correlate with predatory behavior. The ocean contains bioluminescent bacteria that live freely or inside other organisms. Some squid house these bacteria in special organs, using their light for camouflage or communication. The relationship benefits both. The squid gains light, and the bacteria gain a safe, nutrient-rich home. At night, some coastal waters glow when disturbed, as bioluminescent bacteria and plankton emit light in response to movement. This living light show demonstrates the beauty of symbiotic relationships. Red tides are blooms of certain types of algae that can discolor the water. Some species produce toxins that can kill fish, seabirds, and marine mammals. Shellfish feeding in these blooms can accumulate toxins, making them dangerous for humans to eat. Red tides are natural events, but nutrient pollution from agriculture can make them more frequent and severe. This shows how human activities on land can trigger changes in the ocean. Not all algae blooms are harmful. Phytoplankton blooms are essential for ocean productivity. They form the base of the food web and draw down carbon dioxide. Satellite images often show swirls of green or blue-green where blooms occur, visible from space. These blooms follow seasonal patterns, peaking in spring when sunlight increases and nutrients are available. This shows the ocean's rhythm, tied to the turning of the seasons. Diatoms are a type of phytoplankton with cell walls made of silica, forming intricate glassy structures. There are thousands of species, each with unique patterns. When diatoms die, their silica shells sink to the ocean floor, accumulating over millions of years to form deposits called diatomaceous earth. This material is mined and used in filtration, abrasives, and even toothpaste. This shows how ancient marine life has practical uses today. Dinoflagellates are another major group of phytoplankton. Some are photosynthetic, while others consume organic matter. Some dinoflagellates are bioluminescent, creating the glowing waves seen in certain coastal waters. Others form symbiotic relationships with corals. Dinoflagellates can reproduce rapidly under the right conditions. forming blooms. This diversity shows that even within a single group, roles and behaviors vary widely. Coccolithophores are tiny phytoplankton covered in calcium carbonate plates called coccoliths. When they bloom, they turn the ocean a milky turquoise color, visible from space. The White Cliffs of Dover in England are made largely of ancient coccoliths that accumulated on the seafloor millions of years ago and were later uplifted. This shows how microscopic organisms can create geological features on a grand scale. Foraminifera are single-celled organisms that build shells from calcium carbonate. Their shells accumulate on the ocean floor, forming a major component of deep-sea sediment. Scientists study fossil foraminifera to reconstruct past ocean temperatures and chemistry. Different species lived in different conditions, so their presence in sediment cores reveals ancient climates. This shows how tiny organisms serve as archives of Earth's history. Radiolarians are another group of single-celled organisms, but they build their skeletons from silica. Their intricate, symmetrical shapes resemble microscopic glass sculptures. Radiolarian skeletons also accumulate in sediments, and their fossils are used to date rock layers. This shows how beauty and scientific value coexist in the smallest forms of life. The ocean is filled with viruses, far outnumbering all other organisms. These viruses primarily infect bacteria, keeping bacterial populations in check. When a virus kills a bacterium, the cell's contents are released back into the water, making nutrients available to other organisms. Viruses play a crucial role in nutrient cycling, though they are invisible to the naked eye. This shows that the smallest entities can have ecosystem-scale effects. Bacteria in the ocean perform countless essential functions. They decompose dead organic matter, fix nitrogen, and even recycle pollutants. Some bacteria thrive in extreme environments, near hydrothermal vents, in frozen polar waters, or buried deep in seafloor sediments. Their metabolic diversity far exceeds that of larger organisms. This shows that bacteria are not just background players, but central to how the ocean functions. Archaea are microorganisms that resemble bacteria, but are genetically distinct. Many archaea live in extreme environments, such as hot springs and highly salty waters. In the ocean, archaea are abundant in deep, cold waters. Some archaea perform unique metabolic processes, such as converting ammonia to nitrite, an important step in the nitrogen cycle. This shows that the diversity of life extends beyond familiar plants and animals. The ocean contains vast amounts of dissolved organic matter. This is a complex mixture of molecules released by living organisms, everything from sugars to proteins. Some of this matter is readily consumed by bacteria. Other compounds are resistant to breakdown and can persist for thousands of years. This pool of dissolved organics is one of the largest reservoirs of carbon on Earth. It shows that not all organic matter is in the form of living cells. Marine fungi are less studied than their terrestrial relatives, but they are widespread. Fungi decompose organic matter, breaking down wood, leaves, and dead animals that enter the ocean. Some fungi form symbiotic relationships with algae, creating lichens that can live on coastal rocks. Fungi also play roles in nutrient cycling and may help recycle pollutants. This shows that the ocean's decomposers are diverse. Sea ice forms when seawater freezes in polar regions. As ice forms, it excludes salt, creating pockets of highly salty brine that sink into the water below. The ice itself becomes a habitat. Algae grow on its underside, providing food for krill and small fish. Seals rest on the ice, and polar bears hunt there. Sea ice extent varies seasonally and is declining in the Arctic due to warming. This shows how ice, though seemingly lifeless, supports complex ecosystems. Icebergs are chunks of glacial ice that have broken off and drifted into the ocean. They are made of fresh water, not seawater, and can be thousands of years old. Icebergs can be enormous. Some are the size of small countries. As they melt, they release nutrients and sediment, fertilizing the surrounding waters. This can trigger phytoplankton blooms. Icebergs show how land and ocean systems interact. Polynyas are areas of open water surrounded by sea ice. They form where ocean currents or winds prevent ice from forming. Polynyas are biological hotspots in polar regions. Phytoplankton bloom in the sunlit water, attracting zooplankton, fish, seals, and seabirds. These openings in the ice are crucial for the survival of many species. This shows how small variations in ice cover can create oases of life. The Southern Ocean encircles Antarctica, and is unique in that it has no land boundaries on most of its extent. It is the only ocean that flows uninterrupted around the globe. The Antarctic Circumpolar Current, driven by powerful westerly winds, is the largest ocean current by volume. This current connects the Atlantic, Pacific, and Indian Oceans, playing a key role in global ocean circulation. This shows how the Southern Ocean ties together the world's seas. Antarctic krill are small, shrimp-like crustaceans that form the basis of the Southern Ocean food web. They feed on phytoplankton and ice algae. In turn, they are eaten by fish, seals, penguins, and whales. Krill live in enormous swarms that can stretch for kilometers. A single swarm can contain millions of tons of krill. This shows the incredible productivity of polar waters. Leopard seals are predators of the Antarctic. They hunt krill, fish, squid, and even penguins. Leopard seals are solitary and powerful, with large jaws and sharp teeth. Despite their fearsome reputation, they are curious and have been known to approach divers. They show the diversity of hunting strategies among marine mammals. Weddell seals live farther south than any other mammal, breeding on the ice near the Antarctic continent. They can dive to depths exceeding 600 meters and hold their breath for over an hour. In winter, when the sea surface freezes, Weddell seals maintain breathing holes in the ice by gnawing at it with their teeth. This dedication shows the adaptations required to survive in the harshest environments. Emperor penguins endure the Antarctic winter, the coldest season on Earth. They breed on the ice, laying a single egg in the middle of winter. Males incubate the egg on their feet, tucked under a fold of skin, while females travel to the ocean to feed. The males huddle together for warmth, enduring months without food. When the chicks hatch, both parents take turns feeding them. This extreme parental investment shows the lengths to which animals will go to ensure their offspring survive. Adelie penguins are smaller and more numerous than emperors. They breed in large colonies on the Antarctic coast during the summer. Adelies are excellent swimmers, capable of leaping out of the water onto ice or rocks. They feed on krill and fish, diving repeatedly throughout the day. Their black and white plumage provides camouflage in the water, dark above, light below. This shows how even Antarctic species use countershading. Seabirds like albatrosses can travel vast distances without landing. They use dynamic soaring, a technique that takes advantage of wind gradients near the ocean surface. By flying in a specific pattern, they can gain energy from the wind and glide for hours without flapping. Albatrosses can circumnavigate the Southern Ocean multiple times in a single year. This shows the power of flight adapted to the open ocean. Albatrosses mate for life, returning to the same nesting site year after year. Their courtship involves elaborate dances and vocalizations. Both parents share the duties of incubating the egg and feeding the chick. A single chick takes months to fledge. This long investment means albatrosses reproduce slowly, making them vulnerable to population declines. This shows the trade-off between long lifespan and low reproductive rate. Petrels and shearwaters are smaller seabirds that also spend much of their lives over the ocean. They nest in burrows on remote islands and range across vast areas in search of food. Some species migrate between hemispheres, following summer in each. Their ability to navigate across featureless ocean shows the sophistication of avian orientation. The ocean plays a role in global weather patterns beyond just providing moisture. Ocean temperatures influence atmospheric pressure systems, which in turn drive wind patterns. Warm ocean surfaces fuel tropical storms, while cold currents stabilize the atmosphere above them. The interaction between ocean and atmosphere is so tightly coupled that meteorologists monitor sea surface temperatures to improve weather forecasts. This shows that understanding the ocean is essential to understanding weather. The ocean stores heat for long periods, creating thermal inertia. This means that ocean temperatures change slowly compared to land or air. This inertia affects climate on seasonal to decadal timescales. For example, if the atmosphere cools temporarily, the ocean can release stored heat, moderating the cooling. Conversely, once the ocean warms, it takes a long time to cool down. This persistence shows that changes to the ocean have lasting effects. Ocean heat content is now measured using a network of floats. These autonomous instruments drift with currents, periodically diving to 2 kilometers depth, measuring temperature and salinity, then surfacing to transmit data. Thousands of these floats are deployed worldwide, providing a real-time picture of ocean conditions. This shows how technology has revolutionized ocean observation. Tidal energy can be harnessed for electricity. Turbines placed in tidal streams or barrages across estuaries capture the kinetic energy of moving water. Because tides are predictable, tidal energy is more reliable than wind or solar. However, suitable locations are limited, and installation can affect marine life. This shows that the ocean offers renewable energy, though not without challenges. Wave energy is another potential renewable resource. Devices that bob on the surface or sit underwater can convert the motion of waves into electricity. Wave energy is abundant along coastlines exposed to prevailing winds. Research continues into making wave energy devices efficient and durable. This shows that the ocean's restless motion holds untapped power. Offshore wind farms are increasingly common. The open ocean offers strong, steady winds that can turn turbines more consistently than on land. Floating platforms allow turbines to be placed in deep water, far from shore. These wind farms can generate large amounts of clean energy. This shows how the ocean's surface can be used without depleting its resources. Desalination removes salt from seawater to produce fresh water. Coastal regions with limited freshwater supplies increasingly rely on desalination plants. The process is energy-intensive, but improving technology is making it more efficient. Desalination shows how the ocean, despite being salty, can help meet human water needs. Aquaculture, or ocean farming, produces a significant portion of the world's seafood. Fish, shrimp, oysters, mussels, and seaweed are farmed in coastal waters in pens. When done sustainably, aquaculture can reduce pressure on wild fish populations. However, poorly managed farms can cause pollution and spread disease. This shows that the ocean can be farmed, but careful management is essential. Seaweed farming is growing rapidly. Seaweeds grow quickly and require no fresh water, fertilizer, or land. They can be used for food, animal feed, fertilizer, and even biofuels. Some species also absorb nutrients and carbon dioxide, helping to clean the water. Seaweed farms show how the ocean can contribute to food security and environmental health. Oyster reefs once lined many coastlines. Oysters filter water, removing particles and improving clarity. They also create habitat for other species. Overharvesting and pollution destroyed many oyster reefs. Restoration efforts are now underway in several regions, replanting oysters to rebuild these ecosystems. This shows that damaged marine habitats can be restored with effort and care. Salt marshes are coastal wetlands flooded by tides. They support grasses and other salt-tolerant plants. Salt marshes provide nursery habitat for fish and shrimp, buffer coastlines from storms, and trap sediment. They also store large amounts of carbon in their soils. Despite their value, many salt marshes have been drained or filled. This shows the importance of protecting coastal habitats. Estuaries are where rivers meet the sea. The mixing of fresh and salt water creates a unique environment. Estuaries are among the most productive ecosystems on Earth, supporting fish, birds, and shellfish. They also filter pollutants from river water before it reaches the open ocean. Many major cities are built on estuaries, making these areas particularly vulnerable to human impact. This shows the importance of estuaries as ecological and economic centers. Coastal wetlands, including mangroves, salt marshes, and seagrass beds, are sometimes called blue carbon ecosystems. They capture and store carbon dioxide from the atmosphere in plant material and sediments. Per unit area, they store more carbon than forests on land. Protecting and restoring these habitats can help mitigate climate change. This shows that coastal ecosystems are valuable not just for biodiversity, but also for climate regulation. The ocean floor is a repository of human history. Shipwrecks, submerged settlements, and lost cargo lie on the seabed, preserved by cold water and sediment. Underwater archaeology reveals trade routes, ancient technologies, and past societies. Wrecks also become artificial reefs, attracting marine life. This shows how the ocean holds both natural and cultural heritage. The Titanic rests at a depth of nearly 4 kilometers in the North Atlantic. Since its sinking in 1912, the wreck has been colonized by bacteria that slowly consume the iron. Rusticles, formations resembling icicles, drape the hull. Eventually, the ship will dissolve entirely. This shows that even steel and iron return to the ocean, recycled by microbial life. Submarines allow humans to explore the deep sea directly. Early submersibles were cramped and limited in depth. Modern ones can reach the deepest trenches, equipped with cameras, robotic arms, and scientific instruments. Piloted dives have revealed hydrothermal vents, filmed giant squid, and collected samples from unexplored regions. This shows that human curiosity continues to push the boundaries of exploration. Remotely operated vehicles, or ROVs, extend human reach without risk. Tethered to ships, they can stay underwater for hours or days, filming and collecting samples. ROVs have become essential tools for deep-sea research and offshore industries. Their footage has brought the deep ocean to audiences worldwide. This shows how technology allows us to witness environments we could never survive in ourselves. Autonomous underwater vehicles, or AUVs, operate independently. Programmed to follow specific paths, they map the seafloor, measure water properties, and search for objects. AUVs are used in research, environmental monitoring, and even searching for lost aircraft. Their independence shows the advance of robotics in ocean exploration. Citizen science projects engage the public in ocean research. People report sightings of marine animals, classify images of the seafloor, or monitor beaches for plastic. These contributions expand the reach of research and build public connection to the ocean. This shows that anyone can contribute to understanding and protecting the sea. Ocean literacy, understanding the ocean's influence on us and our influence on it, is increasingly recognized as important. Schools, aquariums, and media work to educate people about the ocean. Knowledge fosters appreciation, and appreciation fosters conservation. This shows that caring for the ocean begins with knowing it. Thank you for joining us tonight on this journey through the sea. We hope you found calm in the facts, wonder in the details, and peace in the knowledge that the ocean, vast and mysterious, is always there beneath the stars, beneath the sky, holding life, holding memory, holding time. This has been Deep Somna. If you found this journey restful, consider leaving a like and subscribing for more gentle explorations of the natural world. Until next time, rest well, sleep deeply, and may your dreams be as vast and tranquil as the ocean itself. Good night.